because you could be drinking like full fat.
Time or something?
I don't know.
Does it have a timer on the recorder?
I thought I was recording this.
You can record?
Anyway, I might have just not given you all that good stuff, but I showed it to you. You got the idea. I mean, it's, you know how to do it.
Next time you're gone, I'm not gonna record anything and laugh at you.
Yeah, yeah.
I won't tell you anything.
Actually,
Okay.
Kahoot would be on us because
Guys,
he does
I
everything.
brought Kahoot to the knowledge of Mr. Oya.
You did.
Do that.
You did.
Oh.
Yeah, you did. That was great.
Yeah.
I loved it. That was awesome.
Have you created? Okay, I feel like you're gonna create some bomb freaking Kahoots. You know? See, I feel like you should know that.
If I had time, I would do that stuff. My time is just.
Hey, what
I
if
said
I
no
was your,
time
what
for
if I was
anything.
your aide? I can make Kahoots for you.
Or you could do
Yeah.
more, so he could actually do some good.
Or yeah,
Like, he would not.
I can do all that mundane work like entering in my grades, your class's grades.
Oh, okay.
Yeah.
Okay, so here's what I want to show you today, or at least get started showing you today. I want to show you. We're gonna talk about limits at infinity. We're gonna add a really useful tool, and let me put this kind of, excuse me, in perspective here. So we're adding tools for functional analysis. That's largely what calculus allows us to do. If you think about our table, what does our table do for us? Our table allows us to summarize a whole bunch of information about a function and its derivatives, and use that information to find useful things like where are points of inflection, where are relative extrema, right? Where are intervals of positive and negative concavity, things like that, right? Well, we added one more diagnostic tool today that will fit into our table. And that is, we want to know what the end behavior of a function is. What's the behavior at the tails? So as x approaches negative infinity or positive infinity. And we can break this down into really three pretty simple cases, and then we'll sort of extrapolate one of those to deal with an oddball case. But let's start off talking about rational functions. So rational functions are just ratios of polynomials. Polynomial divided by polynomial, right? And let's look at three cases. Let's look at the case where we've got something like, how about like this? We're going to take f of x equals, let's just do 2x squared minus x plus 1 over 3x cubed plus 4x plus 2. Okay, let's take that one. Well, actually, let's take them one at a time. And let's take the limit of this. What's the limit of f of x as x approaches plus or minus infinity? I want you to think about that and see if you can just tell me the answer, first of all. What do you think?
It's gonna get bigger slowly. Well, because on the bottom, that's going to get bigger faster than the top is. So that means the number is going to get bigger. So it's gonna go down.
It's going to go down.
It's gonna go down.
Okay, let's take an example of a problem here. What if we took something like, let's take, just for a moment, let's just take something like the function, we'll come back to this one. Let's just take something like, I'm going to make something up here. Let's say we've got f of x equals 0.001 x cubed plus 0.1 x squared plus x plus 1. Okay? Let's graph that function in Desmos.
Is that like a Teenage Mutant Ninja Turtle?
You guys know about Desmos, right?
Online calculator that goes on your graphic board.
Yeah, it's awesome.
My 7 years
I'm gonna make that small so I have room to put Desmos up here.
Didn't you have a different graphic calculator program?
Yeah, this is the best one. And this, you're gonna be able to use this on standardized tests now, which is really cool. So let's graph this thing.
Have more standardized tests?
Not until college,
Go college.
unless you failed like your SAT.
No, I did pretty
Or
good on
your
my
OSHA
SATs.
test last year. Did you retake yours? No, I know. You did.
You got 1400, right? Or was it, yeah. Still haven't taken.
Okay, so let's take this function and I'm gonna zoom in.
It's so standard. It tests your patience.
Okay, we're just gonna zoom in. What's this thing start to look like if I zoom way in? Starts to look like what line?
1-to-1 line. Or y equals x line.
Y equals x plus 1. Yeah, okay. What do you know? If I zoom in very closely, it starts to look like the line y equals x plus 1. Okay, well, let's zoom out a little bit. Let's zoom out a little bit here and see what we start to get. What's it starting to look like as I zoom out? Starting to look like a parabola. How about that? Starts to look like a parabola. Good, right? Because we start to see that as x increases, now I want you to see this trend. This is really interesting. So when x is really small, the dominant terms were actually these low terms, right? As x increases, all of a sudden now x squared recaptures the lead. Okay, because x squared starts to grow as x squared instead of as x, right? So it starts to overcome the smaller terms. What do you think is going to happen as I expand out even more as I zoom out? Yeah, all of a sudden it becomes cubic.
Oh, man.
Okay,
Blew my mind.
on a very large scale, so if I get on a really large scale, if I zoom further and further out, this thing starts to look less and less like a linear or a quadratic function, and definitely more like a cubic function. And as I go out forever now, it's just going to look more and more cubic, right? It has all the hallmarks of a cubic function, meaning the end behavior is opposite, whereas it would have been consistent if it was x squared.
If you
Right.
zoomed out enough, would it look like a straight line again? If that little, the shape in the
No.
center?
No, it won't.
No?
It won't. It'll start to look more and more cubic. The part in the middle will get smaller and smaller and smaller,
Like if
but
I got so small that you couldn't see anything like that, wouldn't it just look like that?
no, because this will never be linear, because
How far
this
will that
is
go?
cubic, right?
How far does this
But it would
go?
look-
You should, like,
Say it again.
How far does this program go?
As far as you
Yeah,
want.
how far can you zoom
Can you
out?
keep zooming?
Well, I could, but I don't really need to,
Okay.
because we already got to the point where we can see that it's cubic. So the moral of the story is that if you take a function and you're going to take a limit as x gets big, then the only part that matters is the dominant term, the leading term. The rest of it just becomes background noise, right? Okay? That's important. So then if we go back to this function, we can do the same thing to the top and the bottom, right? In the limit that x gets really big, and that's what we're doing, the top function is going to behave like its leading term, and the bottom function is going to behave like its leading term, right? Everybody see that? So in the limit, this is going to equal the limit of 2x squared over 3x cubed. Okay, so I can simplify that. What happens if I simplify that expression? I get the limit of 2 over 3x as x approaches plus or minus infinity, and what's that clearly gonna be? The top is staying at 2, the bottom is exploding, right? So I get something like 2 over plus or minus infinity, but in both cases, what value am I approaching? 0, right? If the bottom of a fraction gets infinitely large and the top doesn't, then doesn't the fraction get infinitely small as a whole? Right? Okay? So that's the answer. This limit is equal to 0 at the infinity, or at the tails, right? Okay, what's another way of thinking about that? That may seem a little bit odd, so let's talk about infinities for a second. If we look at the top function, yes, the top function is growing, right? It's growing towards infinity as x approaches plus or minus infinity, right? The bottom function is also growing towards infinity, but it's growing towards infinity infinitely faster, right? And so therefore, yes, even though the top is exploding, the bottom is exploding so much faster that it dwarfs the top.
So if it was, for example, 2x squared minus x over 2x squared plus like 4x.
Okay, so we'll look at that in a second.
Okay.
But we could generalize this case, right? If we have a rational function where the order of the polynomial on the bottom is larger, then that always tells you that the limit's going to go to what? 0. Yeah, because the bottom is exploding faster than the top. And so therefore, you end up with a fraction that has an infinitely larger denominator than numerator, which tells you 0, right? And that means then, that tells you something profound about this function. That tells you that if this is the xy plane, it tells you nothing about what happens in there, right? But it does tell you that the asymptotes are going to be, the left and right tails share the single asymptote y equals 0. So this function will eventually, if I go infinitely far to the right, it will approach the x-axis, and if I go infinitely far to the left, it will guaranteed approach the x-axis. That's important. That tells us a lot about the behavior of the function, right? Make sense? Okay. So let's look at another case. Let's look at River suggested a case. What if we have something like this? What if we have f of x equals, let's say, 2x squared minus 1 over 3x squared plus 7x plus 5. And we're going to take the limit of this function as x approaches plus or minus infinity. Okay, what do you think? What could we do here?
Would we need to include some next step?
How come? How could I rewrite this? This is exactly equal to the limit of what?
2x squared over 3x squared.
Yeah, the ratio of the leading terms. Right? The rest of it's just background noise. Okay, so that gives us the limit of 2x squared over 3x squared, and algebraically, what's that equal to? Okay, so that tells us something important. That tells us that this function if I go infinitely far out to the right and the left, it's going to adhere to the horizontal asymptote y equals 2/3. Okay? Make sense? That's our answer. We have shared horizontal asymptotes left and right. Okay. There is, and I'll show you this, but I don't want you to get hung up on it. There is a way you can do this problem algebraically that, maybe you like better. I don't. But it is correct. Well, I mean, just because to me, it's not as elegant. It doesn't seem like it requires more algebra to do the same thing, and therefore I don't like it as well. We could do something like this. If I wanted to take this limit of our first problem we did, I could factor out, I could either factor an x squared or an x cubed out of the top and bottom. Which one does our book prefer to do? Because either way will work. I'll do it the way our book does, just so you've got something. So they take out the bigger of the two. That's fine. So what if I were to factor out an x cubed, top and bottom? On the top, I'd get x cubed times what would be left over if I divided away an x cubed from each term.
2x.
So 2 over x minus
2 over 2x.
1 over x squared plus 1 over x cubed.
Yeah.
Agreed? Divided by, on the bottom, x cubed times 3 plus 4 over x
Squared.
plus 2 over x squared, right? Oh, squared
Squared.
cubed. There you go. Good. As x approaches plus or minus infinity, algebraically I could cancel those. And then now if I took the limit as x goes to infinity, everything with an x on the bottom is going to 0, right? So I end up with the result 0 over 3 equals 0. Same thing, right?
Where's the logic of if x is going to infinity, how is x going to 0?
If x is going to infinity, 2 over x as a whole goes to 0, right?
Oh, yeah.
Right? Everybody see that? So each of these terms is going to go to 0 separately, right? Gets us to the same place, just takes longer, right? I could do, everybody agree? I could do the same thing.
Isn't that just basically saying though that whichever one has the bigger squared?
It
or
is.
The bigger power?
It is, and you don't have to do that, I mean, because now we have a rule, right? What's our rule here? We could summarize this rule into one simple statement. If I take the limit of a rational function where the orders of the top and bottom polynomials are equal, the answer is the ratio of the leading coefficients. Done. Okay? Okay? And then finally, what's going to happen, and you can already tell me the answer, what's going to happen if we have something like, how much time we got? 2 minutes? What if we have something like f of x equals, let's just say we had 4x cubed minus 2x plus 1 over 3x squared plus, or minus x plus 11. We take the limit as x approaches plus or minus infinity. Oops.
When there just be no limit, undefined?
So it's going to be no limit, but we can be a little more descriptive than that. Let's take the limit. Let's do this in 2 parts. Let's take the limit at positive infinity. If I take the limit at positive infinity, once again, I can just look at the ratio of the leading terms, right? So what am I going to get there? I know that I'm going to get the limit of 4x cubed over 3x squared, right? And I know it's going to be infinitely big because the top is growing faster than the bottom. Agreed? We just need to know the signs. As x approaches, okay, we'll finish this one up tomorrow and
I'll keep going.